In today's lecture, we are going to start a very important topic, that is Lyapunov stability. So first we study what is stability. In industrial processes, you have to control many variables. For example, you may be required to control the level of liquid inside a tank. You may be required to maintain temperature of a process at a particular level. You may be required to control and maintain the position of some object at a particular level. So if instead of achieving that particular desired level, the process variable continuously deviates away from the desired level, then that process is called unstable. For example, here is a plot of some process variable, and instead of achieving the desired level, it is continuously deviating away from the desired level. Therefore, this process is unstable. This explanation is just a very layman explanation of stability and instability. You have talked about more formal definitions of stability for linear systems. You have talked about BIBO stability, that is, if you apply some bounded input to a process and the output remains bounded, then that process is called stable process or stable system. You have also talked about internal stability. This internal stability is more a strict condition than BIBO stability. Here we not only require the output to be bounded, rather we also require that all internal signals and states remain bounded. That is consider, for example, this system, and you can easily find the transfer function from this variable and this variable, that is given by this relation. And we can see that this transfer function is a stable transfer function. That is, if we apply some bounded input over here, this output will remain bounded. However, the transfer function from this signal, which is sensor noise, to this signal, which is the control input, this transfer function is given by this expression. We can see that this is unstable transfer function. That is, even if this sensor noise is bounded, this control signal will become unbounded. Hence, this system is not internally stable because some internal signals are unbounded. So you are already familiar with these two definitions of stability, which you have studied in your linear control systems theory. Let's talk about the stability of nonlinear systems. The discussion on stability for nonlinear systems is slightly different. Here we do not talk about stability of systems, rather we talk about stability of equilibrium points, because a nonlinear system may have multiple isolated equilibrium points. Therefore, we talk about stability of each of the equilibrium points. And there are different definitions of stability. The topic of our interest in this course is Lyapunov stability. We shall discuss it in much more details. There are other notions of stability as well for nonlinear systems, that is input-output stability and input-to-state stability. So if we get time, we shall talk about these two concepts at the end of the course, and here we talk about Lyapunov stability in much more details. So what is Lyapunov stability? An equilibrium point of a system is said to be stable in sense of Lyapunov if all system trajectories starting at nearby points stay nearby. So here this phrase needs further explanation. To explain it, we again consider our favorite example of the pendulum system. If you drop pendulum from this position, for example, this pendulum will oscillate about its equilibrium point. The equilibrium point is exactly in downwards position, and after some time the pendulum will settle down at this equilibrium point, provided that there is some friction over here. And here is the plot of system states. This is plot of angular position, and this is plot of angular velocity. We see that after some time these states settle down to the equilibrium point at origin. And here is the phase portrait of the same system. with the state x1 on the horizontal axis and x2 on the vertical axis, that is angular position on horizontal axis and angular velocity on vertical axis. The equilibrium point under consideration is at origin, that is over here, and the trajectories which started from this initial condition near the equilibrium point, and this trajectory stayed near the equilibrium point. Therefore, this equilibrium point at origin is stable equilibrium point. Compared to that, if we talk about this equilibrium point in upright position, we have this situation. So if we drop pendulum from this upright position, it will move away from that equilibrium point. Here is the plot of system states, angular position and angular velocity, and the phase portrait over here. And now the equilibrium point under consideration is in the upright position, that is the angular position equal to pi and angular velocity 0, which is somewhere over here, and the trajectories which started from near the equilibrium point, these did not stay near the equilibrium point, rather these have moved away from the equilibrium point. Therefore, this equilibrium point in upright position is unstable equilibrium point. To be more precise, here is the mathematical definition for Lyapunov stability for a nonlinear system given by this relation, where f is some nonlinear function of state variables. The equilibrium point at origin is said to be stable if for each epsilon greater than 0 there exists a delta greater than 0 such that this expression is satisfied. This definition needs further explanation, so let's talk about these expressions in more details. What is this thing? For a system with two states, this expression, this inequality, describes the interior of a circle. We know that here this norm, which is the 2 norm, we have x1 square of 0 plus x2 square of 0 less than delta square. This expression is another representation of the same statement for a system with two states. So this is interior of a circle. So what does this definition mean? If the trajectories start from within interior of a circle with radius delta, and the trajectories stay inside another circle of radius epsilon for all future times, then that particular equilibrium point is a stable equilibrium point. Here is the phase plane, and in the phase plane this expression represents the interior of a circle, which is depicted over here, circle with radius epsilon, and this inequality describes the interior of another circle with radius delta. So this definition states that an equilibrium point at origin will be stable if corresponding to each epsilon there exists a delta such that all trajectories starting from interior of this circle stay within interior of this bigger circle of radius epsilon. That is depicted over here. A trajectory starting from within this circle stayed within this circle, hence the equilibrium point at origin is stable. Remember that here this word each is also very important. That is, corresponding to each value of epsilon there must exist some delta such that trajectories starting from interior of this smaller circle stay within interior of this bigger circle. So such a delta must exist for each value of epsilon. We again explain this concept with the help of our favorite example, that is pendulum system. Here we have a circle with radius epsilon and another circle with radius delta, and here is the phase portrait for that particular system, the pendulum system, and we see that the trajectories starting from within this circle stay within this bigger circle. all the trajectories starting from interior of this smaller circle must stay inside interior of this bigger circle. We have plotted the trajectories for one initial condition, and here is the plot of trajectories for another initial conditions. So for all possible initial conditions, there are infinitely many possible initial conditions. For all possible initial conditions within this circle, the trajectories must stay within this bigger circle. And also this delta must exist for each value of epsilon. Here is one possible situation, and let's say we take another value of epsilon which is smaller than the previously taken epsilon. Corresponding to this epsilon, there is another delta such that trajectories starting from within this circle stay within this bigger circle. Hence, the equilibrium point at origin is stable. Compared to this, if we talk about the equilibrium point of the pendulum system in upright position, we see that for example, corresponding to this epsilon, we cannot find any delta such that trajectory stay within this bigger circle. Here is one trajectory which corresponds to angular position of 170 degrees and angular velocity of 0. So here is the phase portrait. We see that the trajectory starting from within this smaller circle, they finally leave the bigger circle. And even if we take a smaller radius of this smaller circle, still the trajectories will finally leave the bigger circle. And here is one possible case. So you cannot find any delta except the trivial situation, that is delta equal to 0. So except that trivial situation, you cannot find any radius. For every possible choice of delta, the trajectories will finally leave this bigger circle. So some student may say that if you take, for example, this epsilon to encompass this whole phase portrait, so in that case the trajectory will stay inside that particular bigger circle. But the point over here is that such a delta must exist for each epsilon. And an equilibrium point is unstable if it is not stable. So there are only two possibilities: either the equilibrium point will be stable or unstable. So I hope this definition of Lyapunov stability is very clear. Let's further elaborate it with another example. Our familiar example, van der Pol equation given by these state equations. And we see that for example, corresponding to this value of epsilon, we have taken some delta, and we see that the trajectories finally leave this bigger circle. Whatever value of delta you take, trajectories will finally leave this bigger circle. For example, if we take this delta, even the trajectories starting from within this circle, they leave this bigger circle. So what do you think about the stability of the equilibrium point for this system? So this equilibrium point is unstable because we cannot find delta corresponding to each value of epsilon. One value of epsilon is depicted over here. So even if you find one violation, so that means the equilibrium point is unstable. Here this epsilon is different from this epsilon. Please do not confuse this one, although these are by chance written the same, but these are quite different. So for a system with two states, this thing describes the interior of a circle. So if you have, for example, three states, then this inequality will describe the interior of a sphere, and in higher dimensional spaces it will be a hypersphere. In general, we call it a ball. So if we describe the same definition in our new terminology, that is ball, we have this statement of Lyapunov stability. The equilibrium point at origin is stable if for each epsilon greater than 0 there exists a delta greater than 0, such that the trajectories starting from within interior of this ball, these trajectories stay inside interior of this ball with radius epsilon for all future times. So if that is the case, then the equilibrium point will be stable. This definition, this mathematical expression is exactly the same as written over here, just in another notation. Another very important point is that here in this definition of Lyapunov stability, we have talked about the equilibrium point at origin. So if the equilibrium point is not at origin, we can define a state transformation that will bring the equilibrium point at origin. So this thing does not cause any loss of generality. Even if the equilibrium point is not at origin, we can define a state transformation. Consider, for example, this system, and let's say the equilibrium point is not at origin, rather it is at x bar. So if that is the case, let's define a state transformation. Z is defined to be equal to x minus x bar, and therefore z dot will be equal to derivative of this expression. Derivative of x is x dot, derivative of this constant is 0, and x dot by this equation is equal to f of x. And x from this expression, it is equal to z plus x bar, which is written over here. So this is some function of z, and we can also write this function as g of z, another function of this variable z. So the same system represented in new state variables by using this state transformation is given over here, and we can verify that this new system has the same equilibrium point transformed to the origin. We can verify it. That is g of 0 is equal to f of 0. So g of z is equal to this expression, and g of 0 is obtained by substituting z equal to 0, so which is over here. So we can see that z equal to 0 is the equilibrium point of this system. So this thing does not cause any loss of generality, because if the equilibrium point is not at origin, we can define a state transformation which will bring this equilibrium point at origin. Let's elaborate it with the help of inverted pendulum example. We know that this system has two equilibrium points, one in downwards position and one in upward position. These two equilibrium points, this is already at origin, so we can easily talk about Lyapunov stability of this equilibrium point. However, to discuss the Lyapunov stability, we have to transform this equilibrium point at origin. For that purpose, we can easily define a state transformation, that is z1 is equal to x1 minus pi and z2 equal to x2. Now z1 dot is simply equal to x1 dot, which by this equation is equal to x2, which by this equation is equal to z2, and z2 dot from this equation is equal to x2 dot, and x2 dot is given by this expression. We can rewrite this right hand side in new state variables, and that equation is given over here, and you can verify that for this system, this equilibrium point which was at this location is transformed to origin in new state variables. Another very important point is that instability is different from blowing up. What is blowing up? All the trajectories close to origin move to infinity. For linear systems, instability and blowing up are equivalent, because if a system is unstable, the trajectories will ultimately become unbounded, will approach to infinity. Therefore, for linear systems, instability and blowing up are equivalent. However, for nonlinear systems, blowing up is only one way of instability. It is quite possible that the trajectories remain bounded, but the system is unstable. Here is the example which we have already studied. We can see that the trajectories are bounded. This state x and x dot, these are not becoming unbounded. but still the equilibrium point for this system is unstable. So for nonlinear systems, blowing up is only one way of instability. It is quite possible that the trajectories do not blow up, these do not become unbounded, but the equilibrium point of the system is still unstable.